Good morning and welcome to this next lecture on sound in structural vibration. We are going to start looking at a new topic today, which is transmission of normally incident plane waves through an unbounded partition. Okay, so there is an unbounded partition which goes off to infinity up and down. Okay, and there is a plane sound wave incident on it. There's a plane wave incident on it, and this is mounted on some springs and dampers and so forth, and we want to find out what is transmitted to their side. So let me draw the geometry properly. So this here is my unbounded partition, goes off to infinity in two directions, up and down. This is my x-axis over here, and the partition has a mass m per unit area. Okay, mass per unit area. Okay, it's mounted on springs. The spring stiffness is also S per unit area. Okay, and mounted on viscous dampers, which are also R units per unit area. Okay, and the left side has medium properties rho 1 C1, density rho 1, speed of sound C1, and right side has rho 2 C2. Okay. So now a plane wave is incident. Okay, what's a plane wave? Is just a plane. Wavefronts are plane, no change happens on the wavefronts. Okay, so plane wave is incident. It has an amplitude A tilde for complex, 1 for the medium. Okay, as it hits this this partition, so this partition will obviously start vibrating. Okay, then a sound wave gets reflected, which is with an amplitude B1 tilde, 1 for the medium and tilde for the complex value. And because this partition now oscillates or vibrates, okay, it's a harmonic plane wave, single frequency. So therefore there is going to be a transmitted sound. That amplitude is C tilde and 2 for the second medium. Okay, so we have to find out what is C in this situation. So now let's say the P incident x comma t is given by A1 tilde e to the power j omega t minus k1x. Okay, k1 is the wave number in the left side, k1 is omega by c1. There is a reflected wave given by b1 tilde e to the power of j omega t plus k1x. Okay, so the total pressure on left side. Is given by P, let us call it minus, is equal to A1 tilde e to the power of minus j k1 x plus B1 tilde e to the power plus j k1 x into e to the power of j omega t. Now, let us say the partition oscillates as xi tilde e to the power of j omega t. Okay, that is the displacement. Okay, and therefore velocity is j omega xi e to the power j omega t. That is the velocity. Okay, so at x equal to 0, this is my x as I said, at x equal to 0 where the partition is, if I use my Euler equation, what do I get? Del p minus x comma t by del x is equal to minus j omega rho 1 into velocity, which is j omega xi e to the power j omega t. Okay. Now what is del p minus del x? Again at x equal to 0, what is that value? So if we do that, we get minus j k1 a1 tilde plus j k1 b1 tilde, that is equal to minus j omega, yeah, let me put the time here, rho 1 j omega xi e to the power j omega t. Now I will cancel the time. Okay, then the j, this j can go, this j can go, this j can go, this j can go, then k1 is omega by c1, okay, therefore this can go and this can go. So I have minus a1 tilde plus b1 tilde is equal to minus rho 1 c1 j omega xi, or a1 tilde minus b1 tilde is equal to rho 1 c1 j omega xi. Okay, so this is an important equation. Let us say it is 1. Now the pressure on the transmitted side, P plus, let us say, is equal to the amplitude on the side 2 e to the power of j omega t minus the wave number k2 x. Because the medium is different, the wave number is different. Okay. Now again, if we use the Euler equation, I get minus j k2 c2 tilde is equal to minus j omega rho 2 j omega into xi. Okay, so if we again do the cancellations, minus goes with minus, j goes with j, k2 is omega by c2. Okay, so then omega goes with omega and k2 goes, so I have c2 tilde is equal to rho 2 c2 j omega xi. Now we should not confuse between the C2s. C2 tilde is the pressure amplitude and mere C2 is speed of sound. So this tilde will be the distinguishing factor. Okay. Now we can write B tilde instead of in terms of A tilde. So my B1 tilde is A1 tilde minus J omega rho 1 C1 xi tilde. Okay. So what is the pressure on the negative side, B minus side? What is the pressure? That is given by A1 tilde e to the power minus j k x1 plus A1 tilde minus j omega rho 1 C1 xi e to the power of j k, I'm sorry, this should be k1x, k1x. Okay, so this is k1x. Now I can put the time part e to the power of j omega t. Okay, so if I now add, I get twice A1 tilde cos k1x minus j omega rho 1 c1 xi tilde e to the power of j k1x. Okay, let me put the time here e to the power j omega t and plus j omega t. So that is my pressure on the negative side. Okay. Now let us see what are these two terms. These two terms here we have, what are these two terms? Okay, so this term does not have any partition displacement. It does not have any partition displacement related term. So if the partition displacement is set to 0, if this is 0, then the pressure you would have is this. Okay, so this is just the standing wave. Standing wave that is caused by a incidence and reflection of a plane wave onto a rigid wall or rigid partition. So such a pressure, this pressure is called blocked pressure. Blocked pressure. Okay, and so at x equal to 0, on the partition surface, we get an amplitude of twice A1 tilde plus of course the time term. Now what is this next term here? What is this term here? Okay. So if we separately try to find out, suppose the partition is oscillating at xi tilde e to the power j omega t. Okay. So it will cause a negative going pressure on the negative side. Okay. So the partition is oscillating and therefore it will cause a pressure to go negative. It will cause a pressure to go positive also, but we are not talking about that yet. So this oscillating partition, because there is a medium rho 1 C1 here, will cause a pressure to go leftward. Suppose that is P star e to the power j omega t plus k1x. Suppose that is what it is. Then again if we use our Euler equation, okay, we get j k1 p star evaluated at x equal to 0, okay, and therefore minus j omega rho 1, okay, into j omega xi. This is evaluated at x equal to 0. Okay. So this gives me what? Again cancelling all that, I get P star given by minus j omega rho 1 C1 xi. Okay. So that's what we have here along with the minus. So this expression, now it's worth looking at. This expression P minus involves a pressure term which is the blocked pressure, which can be set due to the rigidness of the partition. On top of it there is a pressure moving leftward due to the oscillation of the partition. So these are the two terms over there. Okay. So my negative side pressure P minus x comma t can be written as twice a tilde cos k1x e to the power j omega t plus P star e to the power j omega t plus k1x. Okay. So this is called the radiated field. This is called the radiated field. Okay. And this is called the blocked pressure, blocked field. Blocked field. Okay. Now so there are pressure, so there is a partition now, there is a partition now, there is a pressure field here, there is a pressure field here, oscillatory pressure fields. There is a partition with mass, stiffness, damping. So we should be able to write a per unit area equation. So that equation of motion per unit area is m xi double dot plus r xi dot plus s xi tilde. Okay. Okay. I have kind of mixed up the notation, I suppose. Let me say xi partition. Okay. Why did I do that? Because I can now say xi tilde partition is xi tilde e to the power j omega t. That is why. All earlier equations were in the terms of this, the amplitude. Okay. So now this is equal to the pressure on the left, which will act towards the right positive direction, and the pressure on the right, which acts in the negative direction. Okay. And therefore, if we use the harmonicity, I get minus m omega square plus j omega r plus s xi tilde is equal to twice a1 tilde minus j omega rho 1 c1 xi tilde minus j omega rho 2 c2 xi tilde. This is being evaluated at x equal to 0. Okay. So if I keep only a1 on one side, I get xi tilde minus m omega square plus j omega r plus rho 1 c1 plus rho 2 c2 plus s is equal to twice a1 tilde. So we will convert it to velocity. So we will multiply by j omega. We will multiply by this by j omega and make it v tilde. Okay. So what we now have is v tilde is equal to, and so we have to divide by j omega also because we multiplied. Okay. So we have minus m omega square plus j omega r plus rho 1 c1 plus rho 2 c2 plus s is equal to twice a1 tilde. Okay, if we now bring this j omega inside, I get v tilde. Okay, then I get r plus rho 1 c1 plus rho 2 c2, and then I get j m omega minus s over omega. That is equal to twice a1 tilde. Okay. Now this, so now the m omega, s by omega and r are the partition impedances, rho 1 c1 rho 2 c2 are fluid impedances. So what this means is that v tilde, the velocity amplitude, is given by the fluid impedance plus the partition impedance operated upon by twice the amplitude. Okay. So zf tilde is the fluid impedance, which is rho 1 c1 plus rho 2 c2, and z tilde partition is r plus j m omega minus s over omega. Okay. So, response of the fluid load at structure is directly related to the blocked pressure. Okay. So, it is interesting. So, the response velocity is directly related to the amplitude of the blocked pressure. Okay. So, we started off by saying we want to know C2 tilde, right. So, that is equal to V tilde into rho 2 C2, okay, which is what, equal to twice A1 tilde by ZF tilde plus ZP tilde into rho 2 C2. Okay. So, if we expand it, if we write it in an expanded manner, we get twice A1 tilde. We expand and divide by rho 2 C2. So, I get R by rho 2 C2 plus rho 1 C1 by rho 2 C2 plus 1, okay, plus J m omega minus s over omega by rho 2 C2. Okay. So, now the transmission coefficient, is given by the tau, given by the ratio of transmitted and incident intensities. So, that is given by C2 tilde square by 2 rho 2 C2 by A1 tilde square by twice rho 1 C1. Okay. Now, this can be written after putting all the expressions. This can be written as 4 times n divided by omega m minus s over omega by rho 2 C2 plus omega 0 m eta by rho 2 C2 plus n plus 1 whole square. Okay, there is a whole squared here also. Okay, where n is given by this ratio, fluid impedance ratio, and the viscous term R has been replaced by m, the natural frequency of the panel, and eta, which is the eta is the in vacuo loss factor, of the panel. Okay. One more thing, that is, we will talk about a sound reduction index, or more commonly known as transmission loss. Okay, symbolized by R as 10 log to the base 10 of 1 over tau, and it comes in decibels. Okay. So, the way to understand transmission loss is that if I have a partition and I am sending a wave, a sound wave, okay, if there is most of it is transmitted, that is of course transmission. Okay. So, transmission is good transmission, good amount is transmitted. However, transmission loss is loss in transmission. Loss in transmission is transmission loss. Okay. If transmission loss is high, then very little got transmitted. Okay. If transmission loss is high, that means very little got transmitted across the partition. So, sometimes you want silence on this side, you have some machinery running on this side and you want silence on this side, which means what? You want high transmission loss, and it is defined in this way. The inverse of transmission itself is an indicator. Okay. So, the time is up for this lecture. I will close, we will start from here. Thank you.